recording's rolling. It is Wednesday, September 3rd. So you guys know yesterday we did lesson 1-1. Today I'll cover lesson 1-2. Tomorrow lesson 1-3. That'll give you guys Friday for time to do homework puzzles and Alex. All right, so guys, we're gonna try something a little different here. So I had a certain idea yesterday how I want to do things, and then after that lesson, I would call and say, okay, actually, I figured out a much better way to do this. Okay. Now I did tell you guys I was gonna give you guys points for taking notes yesterday. So I'm gonna actually do that right now. You guys got your notes out? You guys got notes out? I'm just gonna go around, do a notebook check. If you showed me your notes from yesterday, I'm just gonna make a check next to your name, and then at the end of the class, I'll go put the point in the grade book of that. Instead, a much better idea is this. I picked some puzzles out of each of the first three sections. So the one we did yesterday, one we're about to do today, one we do tomorrow. Actually, I printed them on this little paper. So I will walk around, give you guys this paper, which just has this listed on it. Okay, so these are going to be due on Monday. Now, there's a typo on here. It says August 8th. Monday's actually September 8th. Oops, sorry about that. So Monday, September 8th is going to be the due date for these. Okay, so right now I'm going to pause this video recording. I'm going to walk around, do a notebook check. As long as you show me your notes from yesterday, I'll give you guys points in the grade book. And I'll also give you guys that slip of paper that says what the assignment is due on Monday. And we're back. We're back. All right, so show me your notes for today. Got you checked off, put points in the book. I also gave you guys this. Remember, this should actually say September 8th. Monday, September 8th. Okay. So questions from lessons 1-1, 1-2, and 1-3. All right, we covered 1-1 yesterday. So today let's cover 1-2. All right, so go through the chapter, show you the concepts, and then I'll solve some of these with you guys. All right, so there's a few concepts here. One is linear versus nonlinear functions. Now, one thing that make something a linear function is if all the points lie in a straight line. So if you look at a graph, it's like an XY graph, and all the points lie in a straight line, something like that, for example, you say, okay, well, that would be a linear relationship. Okay. We're on page 15. 15. Yeah, page 15. Okay. Yeah. Yeah, the Homer side of the book. Yeah. So all these questions are out of this book that I'm going through right now. Okay. Now, guys, I'm going to do some really similar questions. Like out of this section that I'm covering today, I assigned you these 16, 18, all the way to 39. Guess those? Okay. Now, I'll cover some similar ones. So I might cover, I don't know the numbers off the top of my head as I'm going through. Maybe like 14, maybe 17, maybe I'll cover number 21. I don't know. So some ones that are similar. Okay. So you'll see a model. Right. All right, so linear. This might be, for example, here, make a better linear function. Okay. What if I graph? So y versus x. Y is equal to, let's say 2x plus 3. So you go up here to 3, there's your y-intercept. Okay. This has the slope of 2. So this has a rise over 1 of 2. So up 2 over 1. Okay. And I can refer to that. Okay. Now, another way to distinguish if something linear is a graph linear is you can get it just by looking at the equation. Right? Because guys, what's the implied power on x and what's the implied power on y? 3 raised to the power of what? 1. Yeah, this is actually x to the power 1, y to the power 1. Right? Guys, what if it was like x squared? Guys, if this was x squared, this would not be a straight line. This would be a what? A parabola, right? Which would not be linear, right? Right. So that's another rule. If your x and y are each raised to the power of 1, right, or 0, because power 0 just goes like a flat line, right, which can also be linear. But raised to the power 0, raised to the power of 1 tells you if something's linear. Right. All right. Okay, identify from graphs. Okay, we just did that. Intercepts. Let's talk about intercepts. So you guys know intercept is where it's crossing an axis. Now there are two axes. That's two kind of intercepts. We have x-intercepts and y-intercepts. Let's look at this example right here. Okay. Guys, how many y-intercepts do you see right here in this function? Yeah, one. In fact, can't the function only have one y-intercept? And what is this coordinate right here? 12. Yeah, 0, 12. You guys see 0, 12 is the y-intercept. Right. Now, what about x-intercepts? Can a function have lots of x-intercepts? Yes. Yeah, in fact, this one has how many x-intercepts? 3. 3. Yeah, so here, see here at -3, 0. I see it -1, 0. I see it 2, 0. I see it when those be the 3 x-intercepts. Right. All right. How about, okay, let's talk about that.
Can I get a checkpoint?
Yeah.
It's only some though.
So,
Oh,
okay, it's pretty good. Thanks.
Interpreting meaning of intercepts. Because if you just have a plain graph like this, okay, great, got y's, got x's, that's really abstract. But you'll see some word puzzles. Right, so what could this apply to? Okay, let's look at Ricardo launching a rocket off the balcony. And I got height as a function of time. So it looks like at time 0, maybe he started launching the rocket. And then it looks like after 8 seconds, there's some story that the rocket goes through. Now, how high was it? Well, it started at 15 feet off the ground, and then it blasted up higher, 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 higher. At 4 seconds, it was all the way up to 210 feet. But after that, it looks like it's coming back down. And at the 8 second mark, it's down to 0 feet, like ground level. You said? Okay. Now, if I sort of draw that out,
Yeah, grab his phone call. Pause this.
all right, we're back recording. We're back. We're back. Okay. So if I sketch this out, I'm going to call this height and feet as a function of time and seconds. Make it look more like a physics type graph. So I'm just taking this information right here for the rocket. So height versus time for a rocket. Okay. Now it looks like at time 0, it started at 15 feet off the ground. I don't think my graph's going to be exactly to scale, but just get the idea. Okay. At the 4 second mark, it went all the way up to 210. So that'd be like a point here. And then at the 8 second mark, it was down to 0. So the point is 0. I mean, those would be 3 points on the graph, wouldn't it? Okay. Now, if I plotted all the other points, there's 9 points altogether. I think it would basically take this shape. Okay. But just get to the point, because the point of this exercise is to interpret what the intercepts mean. Okay? So let's start with this y-intercept right here. So this would be the point 0, 15. Right? That means something in the to this particular scenario. Because what does that mean? That means at time 0, the rocket was at what? Yeah, at elevation 15 feet. Right? Okay, so maybe Ricardo has his rocket on a giant platform. He has like to climb a ladder to He's climb up 15 feet so he can light his rocket and start launching it. At time 0, when the rocket starts launching, it's already 15 feet, way up on this platform. And it goes way up and then it comes down. Yeah. Okay. Here's your other intercept right here at the point 8, 0. That means something too. That means what? At 8 seconds, the rocket, what's happening at 8 seconds? Yeah, is at ground level. You can say it crashes into the ground. Like that could be okay. A few different ways to phrase that. Okay. So basically, something kind of like that, right? Okay. Yeah. So what's the meaning of these intercepts? So if you see a word question. Okay. All right. Oh, next, symmetry. Symmetry. Now, there's different kinds of symmetry. They talk about line symmetry and point symmetry. Now, line symmetry is if you can introduce some kind of line into your relation to your function, and it acts as a mirror, right? Like, you guys see this parabola right here? Like, if I hold my ruler right on this dashed orange line at x equals -1, could that act as a mirror? And see the function flips, mirrors on itself exactly? Right? So, we're going to call that line symmetry. Okay. About the line x equals -1. Okay. Now, if something has point symmetry, that means that you can rotate it 180 degrees around a point and it'll land exactly on itself. Because this looks sort of like a cubit. So let me sketch out kind of a cubic shape right here. Okay. So get some axes going. Okay. But this comes up like this and then it goes on like that. Okay. Does this look very, very, very similar to this example they got going right here?
Yes.
Okay. Now, guys, watch this. What if I put right at the origin point, pop a hole right there? You see it? Okay. What if I flip this 180 degrees? Does that look like the exact same graph?
Yes.
Sure does. Okay, so I can just spin about that point. So that would be, I can rotate 180 degrees about a point. They're calling that point symmetry. Okay? Now, we're going to extend that idea to something called even versus odd functions. Now, I asked my last class, and only one student had ever heard these terms. Guys, who's ever heard these terms? Even function and odd function? Okay, so like 2 or 3 guys maybe. Right, right. So this is very similar to what we were just doing with line symmetry, point symmetry. In fact, it's kind of line symmetry. It's a kind of point symmetry. Okay. So if something is an even function, then that is line symmetry. Line symmetry about the y-axis. The y-axis, by the way, has the equation x equals 0. That is the y-axis. Okay. Okay. And they spell it out here as f of negative x equals f of x. That's to say, whatever's going on the left side of your graph is a mirror image of what's going on the right side. The same thing, right? For any parabola centered on the y-axis has this even symmetry. Let's call it even function. I'll do an example with you guys. Here, I'll take an example that looks a lot like theirs right here. So what if I have a graph, do x-axis, y-axis. Okay. What if I have the graph y equals, or f of x equals, if you like, let's do x squared minus 7, just to pick something. Right, we got it. So, can you guys graph that before I graph it? Can you guys beat me to that? What would that look like? Like, what would the y-intercept be?
-7.
Yeah, 0, -7, right here. So here's 0, -7. That's 1 point. Right? And then what does the rest of the graph basically look like? Right. But let's get another point. Because what if x is equal to 3? If x is 3. If x is 3, what is y? What's 3 squared? Minus 7. Is that 2? That point right there, basically? Okay. What if I plug in -3 for x? What's -3 squared? Still positive 9. Right? Minus 7 is still 2. That point right there? Right? So basically something kind of like this, wouldn't it? Okay. In fact, I'll write out exactly what I just said. I said if I do f of -3, that's -3 squared is 9 minus 7 is 2. If I do f of +3, that's +3 squared is 9 minus 7 is still 2. See how they're the same thing? Right? Can that work if I take any negative x value and its corresponding positive x value? Would I always get the same y value? Right? Well, I can do that by plugging in negative x versus x. What is f of negative x just in general? Well, here, I can try it out. So where the x is, I'll put a negative x. I'm going to square that, minus 7. Right? And then just clean this up and see what it looks like. You guys get the concept? Right. So f of negative x, wherever the x was, I just put negative x. I'm going to run it. So f of negative x is, but guys, if I square negative x, what do I get? Positive x squared. The negative just goes away like it was never there. Right? And look what I have. This bit right here is f of x. So f of negative x is f of x for any value of x. It's the same thing. You see, it has to always is generally the same thing. You see that? Okay. So that's defined as an even function. Whenever you have an even function, you can say it's a mirror image around the y-axis, and this is how you can test it out. Okay. So if you have some crazy function, you're like, I don't even know. Ooh, it's like I got x to the power of 6, and I got 7 times x to the power of 4. I don't know. Just put everywhere you see an x, just plug in a negative x and see if by the time you clean it up, it looks like the original function. Because if it does, that would make it even. Right? Right, so that's even functions. What is this odd function? Now, odd function is kind of what I was doing before with this. Actually, it has point symmetry about the origin. So you can rotate about the origin. It looks exactly the same function.
Oh, Mr. Griffin,
Yeah.
can you put those notes back up?
This right here?
Yeah.
Okay. Like that. Okay. All right, so let's do an example of odd then. So if it's odd function, I could say has point symmetry about the origin, so about 0, 0, the origin point. Okay. And to test this out, this would be f of negative x. All right, so whatever's going on, say on the left side of the graph, you can sort of think that way. Okay. It turns out is f of x, except that it's also flipped upside down. So negative f of x. Okay. Yeah, notice that's subtly different than what I wrote for even. Here's even. F of negative x is f of x. Whatever's going on the left side is equal to what's going on the right side, mirror image. Okay. But for an odd function, left matches right, except that it's also flipped upside down at the same time. Okay. Same thing as rotating 180 degrees. Okay. Okay. So let's do an example of this one. How about x-axis, y-axis? Right. What about y equals x to the power of 3? Right. So, or I could say f of x. Maybe I should write that way. F of x equals x to the power of 3. We do that. Okay. Okay. So let's try it for different values. Okay. You guys ever know if you don't know what a graph looks like, can you just make a table of values? Let's try -2, -1, 0, 1, 2. See what y comes out to. Okay. So how about 0? Okay, so if I plug in 0 for x, what does y come out to? What's 0 to the power of 3?
Yeah.
0, 0, 0. How about if I plug in 1? What's 1 to the power of 3? 1. What's 2 to the power of 3? 2 times 2 times 2. 8. Aha! 8. Okay. Let's go negative. All right, I'm finished off this whole table right here. What if I plug in -1? Now what do I get?
1.
-1. Because negative times negative times negative, like an odd number of negatives, is still negative. Okay. How about if I plug in -2? What do we get? -8. Aha! Okay, so -2, -1, 0, 1, 2. Okay. I put 1, let's put 8 way up here. And -1, -8. Okay. So if I plot those points, looks like that. Sweep a curve through. So there's y equals x cubed, right? Okay. Oh, okay, show of hands. How many guys have seen this before? Does this look familiar? Y equals x cubed? You guys see this? Yeah, yeah. Okay, a bunch of you guys have seen this before. Y equals x cubed. Right. See that? Right. So, would this be an example of an odd function? Well, let's put it to this test right here. We're going to say, is f of x negative x equal to negative f of x? Because if that's true, then that would confirm it is odd. And I think it is, just looking at it. So, try, what is f of negative x? Let's see. Well, that would be where the x is, I'll just put a negative x. So it'd be negative x. And that's to the power of 3. Actually, that's the entire function, right? So if I clean this up, f of negative x is what is negative times negative times a negative? That is a negative, yeah. Right? Because negative is making positive, but then throwing one negative, we're back to negative. Okay. Then x cubed. Okay. But this way right here is f of x, or y if you like. Okay. So therefore, f of negative x is negative of f of x. Yeah, that would make it an odd function. Okay. Where x could be, well, anything, right? And it gave you guys 5 values right here. Right, you guys get that? Okay. Okay, so recap. If something's even, it has symmetry about the y-axis where the left side matches the right side, which looks like f of negative x matches f of x. If something's odd, it has point symmetry about the origin. So whatever's going on the left side is the upside down of what's going on the right side. F of negative x matches negative f of x. Put that there. All right, what else is there? Actually, I think that's all we got to cover there. So I'll do some examples with you guys. I'm just going to go through the sections and solve one here, one there. Okay. So the first section says determine which functions are linear. So let's do, how about number 3 and 4? So number 3, 2x plus y equals 10. Guys, is that linear? Yes or no? Yes. How do you know? What's one way you know? How about this? Guys, what's the power on x? What's the power on y? Yeah, it's 1 and 1. Okay. Whenever you have that, that will always form a linear relationship. Okay. Another, can I rearrange this to make this slope intercept form? Y equals negative 2x plus 10. Can you do that? Okay. And here, I'll sketch a little version of that. Okay. So x, y. So up here at 10, it's going to cross. And then it has a slope of 2. Basically like that. So rise over onto 2. That is that line, right? Okay. But it's definitely linear. Okay. All right. How about number 4? So yeah, so I would say linear. Check. Yes, linear. Yes, linear. Okay. Number 4. Y equals 4x squared. Is that linear? You're right. It is not linear. Okay. And one did give away is the fact that x raised to the power 2. Okay. Actually, I bet you guys know what shape that is. What shape is that? Yeah, parabola. So, sure, about x, y. I bet it looked like a real tall, skinny parabola, wouldn't it? Well, tall, skinny parabola takes off real fast. Okay, not linear. All right. Example 2.
Bro, is it near everybody else like this?
Oh, everybody knows.
Right, so same question, but now you get some graph forms. Okay, now graph is ranked at it, no right away. Let's do 5 and 6. Guys, number 5, is that linear? Yes or no? Nope, not linear. Because the points don't lie in a straight line. Number 6, is that linear? Yes, linear. Because all the points lie in a straight line. And if you craft an equation, x and y would each be raised to the power of 1. Okay. All right. Let's do number 9. Measurement. Number 9.
Yeah.
Table shows function modeling the number of inches and feet. Can this relationship be represented as linear or nonlinear? So here they don't give you an equation and they don't give you a graph. Instead, they give you a table. Okay, get a real good look at those numbers. Let's say however many inches go to the right, maybe go forward some number of feet. I don't know exactly what story we're attaching to this, but just the idea. Okay. Good. Get a good look at that table because I'm gonna ask you guys right now. I want to see show of hands. What do you guys think? Okay. Guys, look at those points just from the table. Okay. How many of you guys think that yes, that is linear? Who says yes, that is linear? Okay. Does anybody say no, it's not linear? Okay, I saw a bunch of hands for linear. So here, real fast, yeah, you guys are right. So yes, linear. Okay. One way you can see is I see the inches are increasing by 1 at a time, and the feet are increasing by 12 at a time, and that's like a constant unit. But if you map that out on a graph, so I'll put number of inches here. This goes up to 4, 0, 1, 2, 3, 4. I'll put number of feet up here, maybe so many inches to the right, so many feet forward. This goes 12, 24, 36, 48. Okay. That's exactly the point. So 0, 0 is the point. That's right here. 112, 224. So 112, 224, 336, 448. Yeah, this point's definitely zip line a straight line, just like you guys said. Okay, so we're good. All right, so you guys good so far? Moving on. This set right here, they want you to find x and y intercepts. So how about number 12? Let's do number 12. Number 12. Okay. Okay. Is this right here? What's the x-intercept on number 12? Looks like these squares are scaled like 4 at a time. Right? Does this cross halfway between -16 and -20? What's halfway between -16 and -20?
-6 or 6.
It's here, -16. Yeah, so we're on number 12. Okay. You guys see where this crosses? Yeah, -18. Yeah. So you can just write -18, or as a coordinate to be -18, comma 0 as a coordinate. Okay. How about the y-intercept? Yeah, at 16 is fine, or 0, comma 16. That's where it crosses on the y-axis, isn't it? Okay. Let's do. Let's see. Yeah, let's do 17 money. 17 money, and number 18 golf is one of the ones that I'm signing to you guys. Okay. So these are similar in the sense that there's some word puzzle, and you have to interpret what the numbers mean. So at the beginning of the week, Axel's parents deposited $20 into Axel's lunch account. The money that AXA had left after each day shown on the table for X number of days, Y is the remaining balance. You can see that exactly in the table. Look, we're starting at day 0, and the days are ticking one day at a time. 1, 2, 3, 4, 5. And look at the money in the account. $20. Ooh, shiny. And down to 16. Oh, down to 12. How's my money? So what did the X and Y intercepts? What are the intercepts and what do they mean? So if I sketch this out, just make it really apparent on the graph. Okay, I'll put dollars up here. This goes 4, 8, 12, 16, 20. And I'll put time in days. On this axis goes 0, 1, 2, 3, 4, 5. 0. So I'll start 0, 0. Okay, so it looks like, where's my pink ink? At day 0, she started with $20. After 1 day, she's down to 16. 2 days, down to $12. 3 days, down to 8. 4, how much do you think lunch costs?
$4.
Yeah, $4. It's at $4 a lunch. Put in her account. Okay. Alright, so intercepts. So this y-intercept would be at 0, 20, and this x-intercept would be at 5, 0. Okay. Now, what do those mean? So, here, I'll take $20, which is the y-intercept, refers to what? You guys would say what? Yeah. Okay. The initial account value, the initial money in the account, something like that. How about 5 days? That's this intercept over here. Should be crossing at 5, 0. Represents what? When AXA has no money in the account. All right, let's do 2021. Number 20. Okay. So you guys remember types of symmetry? There was let's call it either line symmetry or point symmetry. Okay, so number 20 down here. Does this have either line symmetry or point symmetry? Line. Guys, I could draw a vertical line where, and it could act as a mirror.
1, 1.
Yeah, at x equals 1. Guess here how I'm holding this ruler right here? That whole vertical line, x equals 1. Could that act as a mirror? If that was a mirror, wouldn't that function be flipping exactly onto itself? Yeah. So I would say this has line symmetry at x equals 1, which is a vertical line. Isn't x equals 1 a vertical line? Okay, is that okay? Number 20? Okay. How about number 21? Ooh, guys, does this have any kind of symmetry? Yes, what kind of symmetry? Point symmetry. Yeah. Point symmetry. Okay. And which point could you rotate it about 180 degrees and it would look exactly like itself again?
0, 0.
Yeah, 0, 0. So point symmetry about the point 0, 0. Right? In fact, guys, since it is point symmetry specifically about the origin point, that also means it's a what kind of function? Starts with an O. Odd. Aha. It's odd function. Where f of negative x equals negative f of x. Okay. Let's do. Actually, that is the next set of questions right here. Okay, I assigned number 22 to you guys, so I'll do 23 with you guys. A little different. So number 23. 23. Is this even, odd, or neither? Okay. Now, okay, so glance at the graph. It looks kind of close to possibly what kind of symmetry? Yeah, possibly odd, maybe. Although, if you look really close, you see the right side, it goes straight up from the origin. The left side, there's that little hump before it goes down. So it's based on that, what do you guys think the actual answer is?
Neither.
Yeah, neither. I think it's not symmetrical at all. Okay. But the way to test this is this right here. Is f of negative x either equal to f of x or negative f of x, because this would indicate even, and this would indicate odd. Okay? And if neither is true, then it would be neither. And you guys told me it's probably neither. So let's test it out for sure, because the function is x to the power 3 plus x to the power 2. So what we want to do is in place of the x, plug in negative x. I want to see what is f of negative x. And see, is it exactly the original, in which case it would be even? Is it exactly the negative, in which case it's odd? Or is it neither? And I think the answer is going to be neither. So, based on the graph. Right? So let's plug in negative x here, and then keep that, and plug in negative x here, and square that. You guys got that? Just wherever the x is, just put a negative x. We're going to test that. Okay. So f of negative x is, okay, because what is negative x all to the power of 3? Yeah, it's negative x to the 3. But what is negative x squared?
Positive x.
Positive x squared. Is that true? Okay. Now, if you look at this right here, okay, is that okay? You're comparing that to this right here. You're comparing f of x to f of negative x. Are these exactly the same? Yes or no? No. In which case, it's definitely not even. Okay. Is one exactly the negative of the other, like the upside down? Also, no. In which case, it's not odd. So it's neither even nor odd for that reason. Okay. Which again, you can probably figure out from the graph anyway. Okay, guys. All right. Let's do at least one of these. Determine whether the equation is linear. Okay, and then determine is it even odd or neither. Okay, so it's pretty similar to what we're doing. I decided you guys to do these 26 and 30. So I'll do with you guys. How about number 29? I'll do with you guys. 29. Okay. So it says y equals 3x squared minus 1. Okay. Can you guys imagine in your head what that graph looks like? Yeah, somebody tell me while I'm finding my ruler. What does that graph look like? Aha, parabola. Yeah, it would be, wouldn't it? Okay. So sketch it out real fast. Okay. So x, y. Okay. Now, minus 1, I know it has a y-intercept down here, -1. And then, well, 3x squared, it's basically some version of this, isn't it? Does look like that. Now, guys, from that picture, does that look like it has any kind of symmetry? Yeah. What kind of symmetry? Yeah, I think it's line symmetry about the y-axis. And actually, line symmetry about the y-axis. So line symmetry about the y-axis. Okay. It is also called a what kind of function? Even function. Okay. But let's put this to a proper test. I would say if f of x is 3x squared minus 1, what is f of negative x? Because if it's exactly the same thing, then that would also indicate an even function, which I think it is based on the graph, but we're going to find out for sure. So where the x is, I'll put a negative x. Is that true? So that. Okay. Hey guys, what is negative x squared? Just x squared. Okay, so I got those 3. So hey, here's f of x. Here's f of negative x. Are those exactly the same thing?
Yep.
They are the same. In which case, yeah, it's definitely an even function. It passed that test. It's an even function. Is it? Right? Yes, sir? All right. I'm going to do one more with you guys. Okay, so I assigned you guys number 35 basketball. I assigned you guys number 38 volume. I'm going to do number 37 with you guys, and then you'll have you'll have a few minutes at the end of class. So if you make up anything, ask me any questions, anything like that. Okay. So number 37, last one today for the notes. Playground shape is shown. The total perimeter is 500 feet. Okay. Now this is okay, so here's a scenario. Okay. Maybe we're sort of constrained. Maybe we got a budget for fencing, and we're able to buy 500 feet of fencing material. And then there's some other kind of geometric constraint where it's got to look some version of this. Okay, kind of copy what they have here. Okay, pretty close to that. Okay, where this is allowed to be 10 feet and this is 5 feet. Okay, we're going to call this x and this y. And okay, with this 10, this 5 in place, and I'm constrained by 500 feet of fencing. Okay, there's lots of shapes I could make. Like I could make this wide and skinny. I could make it, or I could make it wide and like not too far deep. I could make it it's like skinny but deep. Okay, so there's lots of shapes this could take. Okay, but we can make this into an equation. In fact, that's exactly the first question, part A. It says write an equation that relates x and y. Okay. See if you guys can do this first before I give it to you. Can you guys write an equation that relates x and y?
Yeah.
Here, help you guys out. Okay. Guys, what is this side equal to right here? Huh? Y plus 5. Y plus 5. Is it true it has to be this y plus this 5? Y plus 5? And what about, guys, what about this side right here? X minus 10. Yeah, x minus 10. Okay, because here's the whole x minus this 10. X minus 10. Is that true? Okay. I think I have all the sides labeled now. Boom, 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 boom. Got them all. Okay. So the perimeter is just all knotted up. Okay. So the perimeter, which by the way, I know comes out to 500 feet. So I'll just call it 500 feet. Okay. Isn't that the sum of all the sides? So let's see, I got a y here. Here, I'll add this one, y plus 5. I got this x. I got this x minus 10. I got this 5 and I got this 10. Isn't that all 6 sides added up? Add up to 500? Is that right? Okay, so here, let's clean this up. So 500 equals, okay, well I got 2 y's. I got 2 x's. And then let's go away. That 5 and 5 makes 10. I think that would be like that, right? Is that cleaned up a little bit? Okay. Let's keep going. Can I put this in slope intercept form? Like y equals mx plus b, sort of? Okay. Let's get all. You know what? Before I move on, well, I got these 4 terms. Can I divide everything by 2? Is that okay? Probably do that. If I don't do it now, I'll probably have to just do it later. We did that. If I divide everything by 2, it's just like 250. This is just plain y, this is x, and this would be 5. Divide everything by 2. Okay, let's keep the y over here, subtract this over. So y equals negative x plus 245. Okay. So there's y as a function of x. Okay. Again, this playground fencing shape can take lots of individual shapes, but it's constrained. Okay. So for example, suppose this was constrained between 2 buildings and x can only reach 100 feet. You guys got that? Guys, everybody look up here. Everybody look up here. Think about this. Guys, what if x is locked into 100 feet? You guys got that? If x is locked into 100 feet, I can't make it wider than 100 feet. What is y equal to? 145. Because if I plug in 100 right here for x, isn't y 145? Right? So if I made a graph, there's one point that's if x is 100 feet, y has to be 145 feet. Okay. Because if x is getting bigger, what's happening to y? It's getting smaller, because you're subtracting off the x, right? Here's that. Here's another way you can write this. Y equals 245 minus x, if you like. Isn't that the same thing? Okay, so however you like it. Okay. Okay. So, guys, is that equation linear? Yes or no? Wait a minute. Guys, what's the power on this x and what's the power on this y?
No.
Yeah, they're both 1. Right? Here, I'll draw the graph for you guys. Draw the graph. So x-axis, y-axis, we're going y equals negative x plus 245. So 245 up here. So if x is 0, y would be 245. And then this comes down like this, so the negative 1. So if y is 0, x is 245. Graph the equation. Oh, yes, we just graphed it. See where the graph has symmetry? Well, okay. I mean, it's 37. So there. Okay. Yeah, this could technically have point symmetry. Like you could pick any point and you could rotate it 180 degrees and it may not tell. So technically you have point symmetry. Okay. All right. So we leave on that note. Next up here. We've got a couple minutes left. So if you guys have any questions about anything, I will walk around and help you guys out.